Hi students, we are starting a new chapter. In this chapter, we will be discussing energy and matter. To start, we will describe matter in terms of what it is composed of, what state it is in, and how it changes. Now, if something is not matter, then it is energy. So we then will transition to talk about temperature and energy and nutrition. Matter is defined as anything that has mass and occupies space. So literally everything you can think of in the space around you now is matter. That table, that computer, it all has mass and occupies space. Now anything else, you can classify those things as energy. Since so many things can be described as matter, we like to classify matter into different aspects of it. So the first type of classification we want to talk about are what matter is made up of. In this categorization scheme, we have things that are called pure substances. And a pure substance is something that has a definite composition. Often they have atoms that are held together by bonds. When you have substances that are mixed together, however, you now have a new category called mixtures. In a mixture, things are physically mixed together, but not always chemically bonded together. And because of that, in a mixture, the ratio may vary. So a prime example of a pure substance is the table salt that you use to flavor your food. In table salt, there are sodium atoms and chloride atoms. For every sodium atom, there is one chloride atom. It is the 1-to-1 ratio, and they are bounded together in a bond that's called ionic bond, and we will discuss this later on in a few chapters. Whereas in a mixture of roasted garlic salt, you may have some roasted garlic chunks in there and some salt in there. Those roasted garlic chunks are not chemically bounded to the salt. Now you may even vary the concentration of salt. You may have one with less salt or one with more salt. That is a mixture. Within these categorizations, there are subcategories. When we are talking about pure substances, we can describe it in two different types. One is elemental and one is compound. An elemental pure substance is a substance that contains only one type of atoms, whereas a compound is a pure substance, but that substance is composed of multiple types of atoms. So, for example, if you have a pure penny, back in the day, a penny is actually made purely of copper. Seen here, zoomed into the molecular view, you can see that this penny is made up of repeating units of copper atoms. It has only one type of atom, and that atom is called copper. So this is an elemental pure substance. Whereas if you zoom into water, water is a compound that is composed of 1 part oxygen and 2 parts hydrogen. We call that a pure compound. So let's try and analyze an aluminum can. How would you describe an aluminum can? Is it an elemental or is it a compound? If you said it was elemental, you are correct. If you zoom into this aluminum can, you can see that it is made purely of one type of element called aluminum. How about this? Hydrogen peroxide. Looking at the zoomed in molecular view of what hydrogen peroxide is, you should be able to classify that as a compound. It is a substance that is 2 parts oxygen and 2 parts hydrogen. In fact, the oxygens are bounded to each other and each oxygen has a hydrogen bounded to it. That is a compound. Another classification between compound and element is that you can separate a compound out, but an element cannot be broken down to smaller units. So for example, as we said, sodium chloride is a compound. Now you can go through a chemical process that breaks these two apart into its fundamental sodium and chlorine. When you break it up into sodium, it is sodium metal, and when you break it into chlorine, it is chlorine gas. Sodium metal is in its elemental form, and chlorine gas is also in its elemental form. When you try to reduce metal down further to a more basic unit, it is still sodium metal. When you want to break down chlorine gas down to a more basic unit, it is still chlorine gas. So these two are its elemental state. It cannot be broken down any further. Now this property of chemistry is what allows for the variety of molecules that are in existence. When an element is combined with an element, it creates a new substance that does not necessarily have to have the properties of its original substance. For example, sodium chloride is totally edible, while sodium metal and chlorine gas are not things you want to eat. Sodium metal, for one, is very explosive when it is in contact with water, and chlorine gas is actually a poisonous gas. Let's move away from pure substances and talk about mixtures. To start talking about this, I have two images here. Both of these are beakers of water, where in the first case, that water is mixed with oil, and in the second case, that water is mixed with a red, sugary powder. Let's first talk about the red mixture. The red mixture is what we call homogeneous mixture or homogeneous mixture. In a homogeneous mixture, the composition is uniform throughout. That means if you took a sip of the solution from the top, it will taste the same as this solution at the bottom. Anywhere you take a sample of the solution, it is the same throughout. The ratio between the powder versus the water is the same. If it is sweet up here, it will be sweet down here. Another characteristic of a homogeneous mixture is that the different parts cannot be seen. You cannot see the red powder from the clear liquid water. Now, the solution on the left, you can see those parts differently. You can see that there's more concentration of oil here and less concentration of oil here. In this mixture, we call it a heterogeneous mixture. In a heterogeneous mixture, the composition varies from one part to another. You can almost say that it is a mixture that is not very well mixed, that the different parts are visible. So here's another example looking at it from a molecular view. If we take copper pennies and drop it in water, we can classify that as a mixture of water and copper. Now this is an example of a heterogeneous mixture because you can see clearly where the water is, and you can see clearly where the copper is. What about brass? Brass turns out to be a metal that is composed of copper and zinc. You can vary the ratio of copper and zinc to make different types of brass. So that's why this is not necessarily a compound, but a mixture of copper and zinc to make brass. Now you can't tell just by looking at it which part is the copper, which part is the zinc. So that's why this is called homogeneous mixture. Let's try to do some examples to clarify this idea. Number one, noodle soup. How would you classify noodle soup? Noodle soup is heterogeneous mixture because you can see the noodle apart from the soup. Vinegar, which turns out to be acetic acid and water. Vinegar is homogeneous mixture. Homogeneous because you cannot tell where the acid is and where the water is. They are very well mixed together. How about iron nail, which has the symbol Fe? Iron nail is element because it only has one type of atom in it. What about iron rust? Iron rust has a formula of 2 particles of Fe for every 3 particles of O, which is oxygen. That is a compound. It is a pure substance that has 2 elements in it that is in fixed amount. Let's have a check of our understanding. Which of the following is a pure substance? Sugar, a piece of garlic, orange juice, or sriracha hot sauce? Hopefully you said sugar, because in sugar there is only one compound, and that compound is C12H22O11. Even though it looks complicated, it is just one single compound. So it is a pure substance. Whereas a piece of garlic may have many compounds in it, many organic compounds in it. And in orange juice, there's definitely water and also vitamin C and other organic compounds in orange. Same thing with sriracha hot sauce. You can see the ingredient list to know that it has more than one thing in it. Now let's talk about other ways to classify matter. Another way to classify matter is to segregate them into physical states. We have 3 physical states: solid, liquid, and gas. What's the difference between these 3 states? Let's think about it in terms of the shape, the volume, and the attraction or movement of these particles in the different states. Let's first talk about the state of solid. And a prime example here is a piece of rock. Looking at a piece of rock, you may not know this, but the atoms are very tightly packed together. In a solid, the atoms are very packed together. They have high attraction to each other, and because of this high attractions, they are not moving much. Even with a lot of energy, the only thing they can do is vibrate. They cannot move. Because of this lack of movement and high attraction to one another, the shape of solids do not change. They have a definite shape. Sure, when you break a rock, that piece of solid may shatter and become more pieces of solids, but you don't see it flowing from one shape to another. And for sure, the volume of a solid does not change. And now transition and think about liquids. Now in a liquid, the particles now have more energy to move about than they do in the solids. They have more energy, but still the attraction between the molecules are still very great to keep them together. So the particles are still close together. So between this balance is the reason why the shape is whatever its container is in. You can almost imagine this like a bunch of ants. Have you ever seen ants hanging on to one another? Imagine water molecules or other compounds the same way in its liquid state. They're still attracted to each other, so they're clinging on to each other, but not so much that they can't move. They can still move about each other, changing shape. But even in that movement of changing shape, they do not change its volume. Imagine water. When you pour water into a glass, the gravity pulls some water molecules down. At the same time, the water is attracted to other water molecules clinging onto one another. Once it settles into the glass, it spreads out and has that new shape, but still contains that volume. Now, when we move on to gases, it's totally different. In gases, particles move very fast. They have a lot of energy, and because they are moving very fast with high energy, they may break the attraction between each other and be very far apart. And that is why the gas has no definite shape. It takes the shape of whatever container it is in. If it is in a balloon, it takes the shape of a balloon. If it is in a tank, it takes the shape of a tank. If it is released into the atmosphere, it takes the shape of the entire atmosphere. It also fills the volume of whatever container the volume has. And that's why gases can be compressed. It has so much space that you can push them closer and closer together in a smaller space. To summarize the states of matter, I like to give you a molecular perspective of what we just discussed. If you go to fed.colorado.edu, you can see a simulation of the states of matter in its molecular view. So for example, we have here, I've chosen oxygen. So in its solid state, at negative 242 degrees Celsius, it holds its shape. Even with gravity, this does not flow down into its container. It holds the shape of a solid. And you see how it's vibrating? This is to signify that there is some energy in there, and the molecules are moving. We do not see it from our eyes, of course. This is at the molecular perspective. Now when you go to liquid, it starts to kind of flatten out into the container that it is in. You can see that the molecules are still attracted to one another. You don't ever see one molecule just floating around somewhere else. Now if you give it more energy by increasing the heat here, you will be able to break away from this attraction from each other and giving you the gas phase. And in the gas phase, the molecules are really far apart from one another. Now let's look at another molecule that we are familiar with. Let's go with water. In the gas phase, water is moving all about, filling this whole container with water molecules. Now this is moving a lot faster than the oxygen example because our temperature here is very high. What does water look like when it's a liquid? The water molecules now are condensed down and they are attracted to one another. They are very close to one another. They do take the shape of their container. What about the solid? Now in a solid, the molecules are not moving as quickly. Okay, so you can play around with that more if you like. Now let's talk about properties of matter. And in this, there's two categorization of properties. One property is called physical property, the other one is called chemical property. Let's start with physical property. A physical property are the characteristics of matter that is observed or measured without affecting its identity. So when you make that measurement, you do not change the identity of that substance. Examples of this are when you talk about the shape of something, the physical state, whether it's solid, liquid, or gas, its density, or its color. When you describe these things of a matter, it does not change its identity. So for example, if you have copper pipes, what are some physical properties you can say about it? You can say that it is a reddish-orange color, it is shiny, and at 25 degrees, it is a solid. You can also say that its melting point, and it has a boiling point, and it's an excellent conductor of heat and electricity. When you make an observation that its melting point is 1083 degrees, it does not change its identity. It could be a solid and then become a liquid, but it's still copper. And in that last example, we just touched upon what we call physical change. And a physical change is a change that does not involve changing the chemical identity of a substance. Again, for example, if you have a copper pipe and it bursts open, its shape has changed, but it's still copper. Some more examples here. If you take that copper and you melt it down, so from a solid down into a liquid, it has changed state, but it is still copper. Therefore, that is a physical change. And if you take that liquid copper and reshape it and reform it into copper wires, solids here, you again have changed its state, but not its identity, so that is a physical change. Opposite of physical property and physical change are chemical properties and chemical change. So a chemical property is a characteristic that describes the ability of a substance to change into a new substance. Examples of this are flammability, acidity, and reactivity. A chemical change is a change that results in a new substance with a new physical and/or chemical properties. Some examples of this are when you have metals tarnishing over time. That metal was once, let's say, iron, now it rusts and it becomes iron oxide. Notice that the substance is no longer the same. So that is the prime example of a chemical change. Other examples are sugar caramelizing. In sugar caramelization, sugar transforms into caramel. Or when oxygen is burning. A trivia question for you. Which of these images represent the true color of the Statue of Liberty when it was given to the United States by France? Yep, it turns out that the true color of the Statue of Liberty is the left image here. The true color of the Statue of Liberty in its original state was this golden color because it was coated by a layer of copper. Over time though, this copper tarnishes, reacting with water vapor and carbon dioxide in the air, giving us a new compound. And this new compound turns out to be a greenish color. So this is a chemical change. You no longer have elemental copper, but a copper compound, which is a new substance. Again here, we talk about sugar caramelizing and oxygen burning. Again, I would like you to practice seeing things from a molecular perspective. Drawn here, can you classify each of these steps as either a chemical change or a physical change? Looking at the first chamber here, you see that there are two types of compounds. One is 2 red atoms and the other one is 2 blue atoms. Some kind of change occurred and this is the result. And what is the result? You notice that there are a new compound that is 1-to-1 ratio of the red and the blue. And then there's another compound here that is still the blue. And that's because this compound is left over here. As you see that the blue compound is in excess over the red. So how would you classify this change? Yep, this is a chemical change because you have created a new chemical compound. Very good. How about from this step to this step? How would you describe the change? In one chamber, I only see the blue compound, and in the other chamber, I see the blue-red compound. Okay, so this is a physical change because you have not created anything new. You basically separated the two molecules into two different chambers. So we round out our discussion on matter. Let's talk about now the other side of the coin, which is energy. And before we talk about energy, let's talk about temperature. Temperature is a measure of how hot or cold an object is. And we can see that temperature can be measured in the lab using a thermometer like this. Temperature of your patient can be also measured if you want to know whether the patient has a normal range of temperature or if she has a fever. Now you may notice here there are two important temperature scales. The Fahrenheit is what is used in the United States, whereas the Celsius is used around the world and in the sciences. And so as a health professional, you must be able to translate between these two temperature readings. For example, in the Fahrenheit scale, 98.6 degrees is the normal body temperature, whereas in Celsius, that's 37.0 degrees. The first temperature scale was created by a scientist named Fahrenheit. He saw how mercury expands in a tube depending on the temperature environment it is in. First, he took a reading at the freezing point of water and the boiling point of water, defining this at 32 degrees and separating it by 180 degrees apart. And as you can see, those numbers aren't very rounded, so we have an improvement from Celsius in the Celsius scale, where now the freezing point is defined to be 0 and the boiling point of water, whatever that temperature is, we have called that to be 100 degrees. Now in this case, we have divided the difference between freezing and boiling a point of water by 100 degrees Celsius. And that's why another term that you may hear when talking about Celsius is centigrade, because of the 100. So because of this, we must have an equation to be able to convert between the Celsius and Fahrenheit. And here it is. To convert from Celsius to Fahrenheit, you take the Celsius temperature, multiply that by 1.8 plus 32. A note of sig figs is that 1.8 and 32 are exact numbers, so they do not have sig figs. So your sig figs only come from your temperature that you plug in. With a rearrangement of the equation, you can also solve for the temperature in Celsius if you have the temperature in Fahrenheit. So do the rearrangement and you should get this equation, where if you take temperature in Fahrenheit, subtract 32 from that, divide that by 1.8, you will get the temperature in Celsius. So let's now do an example. A person with hypothermia has a body temperature of 34.8. What is the temperature in degrees Fahrenheit? So you will be given this equation. You do not have to memorize it. You simply have to plug in 34.8 to Tc. Doing this computation, you should arrive at 94.64. Again, thinking about significant figures, our original number here has 3 significant figures, so our temperature in Fahrenheit should also have 3 significant figures. That gives us 94.6 degrees Fahrenheit. Now the Celsius was an improvement on the Fahrenheit, but it wasn't good enough. A big flaw of the Celsius is that things can get colder than 0 degrees Celsius. You can have sub-zero temperatures. And in fact, you can go down as low as negative 273 degrees Celsius. It doesn't go down lower than that, so there is a limit. Because of this, there is a new temperature scale called the Kelvin. And the Kelvin scale takes advantage that there is a lower limit and setting that lower limit to become 0. Because the lowest temperature you can ever have is negative 273, which is defined as 0 in the Kelvin scale. So if you add 273 back, you actually comes back to 0 degrees Celsius. The freezing point of water then is 273 Kelvin. Notice that I said 273 Kelvin, not degrees Kelvin. In the Kelvin scale, there are no degrees sign. Again, in the Kelvin scale, there are no negative temperatures, which is why it makes the math super good, and that is why it is the SI unit for temperature. Another name for that lowest degree temperature at 0 Kelvin is called absolute zero. It turns out it's a theoretical limit. We have never been able to measure this limit. So conceptually, what does absolute zero means? Remember I said that temperature is related to movement. The hotter you are, the more movement you have. So imagine at high degree and decreasing that temperature down. The more you go down, the slower you move until you're just holding still and just vibrating. At the point where you do not even have molecular vibration, you are at absolute zero. Now this is why there is a bottom limit to this temperature, because think about how can you move less than when you're not moving at all. That is why there is a bottom to the temperature. All right, to end this discussion on temperature, you would need to know how to convert from Kelvin to Celsius, knowing that the Kelvin scale is basically Celsius plus 273, or vice versa, Kelvin minus 273 is Celsius. Now let's move on to properly talking about energy. Now energy is a hard thing to define. Our best definition for it right now is the ability to do work or to produce heat. Work in this case does not mean something you do to get money here, but work in the sense of science is the ability to move an object. If you take a pencil and you push it, you have done work. Energy can further be described into 2 categories. One is kinetic energy, and this is the energy in motion. So for example, when you go bungee jumping, as you're jumping down, that's kinetic energy. Water flowing over a dam, or when you're lifting weights. The other type of energy is potential energy. Potential is a problematic word because a lot of students may think that it has the potential to become energy. No, it is already energy. It is stored energy. So an example of that is before you're bungee jumping, you're standing at the top of that bridge. Because of gravity, you have that potential energy. Same thing here. Water at the top of the dam has that potential energy. Chemical bonds in food is an example of potential energy. Another principle of energy is that it cannot be created nor destroyed. It can only transfer. When water is standing on the top of that bridge, it is potential energy, but it transforms into kinetic energy as it flows down that bridge. Same thing, the food is your potential energy, and it transforms into kinetic energy as you are lifting weights. Well, now we have to find work. Let's define the other part, heat. Heat, as defined, is the transfer of energy associated by thermal interaction. So you have this interaction in your daily life. For example, if you're holding an ice cube, your hand is warm, the ice is cold, heat from your hand will flow into the ice cube, melting it. That's called a heat transfer. And one of the principles of heat transfer is that it always flows from hot to cold. It never flows the opposite direction. In this example, heat will always flow from the hand into the ice. It will never happen where if you hold an ice cube that is colder than your hand, that heat from the ice cube flows into your hand, making the ice colder and your hand warmer. As stated before, when we were talking about temperature, heat is also associated with motion of particles. The more heat you have, the more movement you have. The lower heat you have, the less movement you will have. Heat is symbolized with the letter Q. So when I say that heat is leaving your hand, you can say that a certain amount of heat is leaving. That certain amount will be a negative number. Whereas if heat is entering into the ice, that heat is positive. Now again, due to the conservation of energy, heat cannot be created nor destroyed. It can only be transferred. So you can say that the heat Q of the hand is equal to the negative heat of the ice, right? That means whatever heat that is given from the hand is received exactly by the ice. So if you imagine, let's say 5 units of heat was gained by the ice, if you put 5 in here, making this Q of hand is equal to -5, meaning that 5 units of heat escaped from the hand. This idea becomes important when we are talking about calorimetry in the lab. Now I've been using the vague word of heat unit. Well, let's now talk about how to measure heat. The SI unit for heat is joules or calories. A calorie is defined as 4.184 joules exactly. And this amount of heat as unit was first measured by measuring how much heat it takes to raise the temperature of 1 gram of water by 1 degrees Celsius. Another note about the unit of heat is that in the United States we use the word calorie kind of misleadingly. We say it in a capital C. If calorie is capitalized, it actually means 1,000 of the lowercase c calories. So a big calorie is equal to 1 kilocalorie. Speaking of calories, let's talk about the energy in our nutrition. If you wanted to do some physical activity like swimming, which is kinetic energy, and it must come from somewhere. So before that, you need to eat. So for example, you can eat this veggie burger, which has 620 calories. And that calorie, which is potential energy, is stored energy, can be transformed into kinetic energy as you are swimming. Now we talk about the energy in food, but how was this measured? The energy content in our food is measured using an instrument called a colorimeter. In a colorimeter, you take a piece of food sample and you burn it. When burning that, it breaks the bonds in the food chemical, which is stored energy, potential energy, and transforming it into heat. That heat heats up a wire that then heats up a water bath. Depending on how much temperature of the water rises, we can back calculate that to calculate the amount of calories released from that food. And so at the end of that, you get some calories counting. In this case, for example, crackers, you would have 120 calories, or in kilojoules, it's 500 kilojoules. So that is a rigorous and experimental way to obtain the energy in food. There is also a general and mathematical way to obtain the calories in your food. Because as it turns out, the energy in food comes from 3 types of macromolecule: carbohydrate, fat, and protein, as seen in this table here. Among that, fat is the most densely caloric. For every gram of fat, there are 9 kilocalories. For every gram of carbohydrate or protein, there are 4 kilocalories. Let's take a look how to use this by calculating the energy in a banana. From this chart here, you will see a medium banana has 26 grams of carbohydrate, 0 grams of fat, and 1 gram of protein. So you take 26 grams, multiply that by 4 kilocalories per gram, 0 times 9 kilocalories per gram, 1 times 4 kilocalories per gram. Summing that up in terms of calories will give you 110 kilocalories. You can do that for other foods as long as you know how many grams of carbohydrate, fat, and protein it has. So let's take a look at an example. A cup of whole milk contains 13 grams of carbs, 9 grams of fat, and 9 grams of protein. How many kilocalories does a cup of milk contain? And it says here to round the final answers to the tens place. So again, I first write my equation of summing up each of the individual macromolecules, carbs, fat, and protein, 13 of carb, 9 of fat, 9 of protein. Plugging in the energy values. Remember that carb is 4 kcal per gram, fat is 9 kcal per gram, and protein is 4 kcal per gram. When you multiply this out, the grams and the grams will cancel, grams and grams cancel, grams and grams cancel, giving you units of kcal for all three numbers. Then simply sum those numbers up. It says to round your final answer to the tens place, so we have 170 kcal. Alright, I would like to round out this lecture with talking about calories intake and output. Another title for this is How to Lose Weight. No matter how many gimmicky diets there are out there, the main principle of losing weight is the principle of pure math. You will gain weight as calories are stored as fat when you intake more than you output. Okay, so a person can only lose weight when food intake calories is less than energy output calories. This is a table of typical energy requirements for adults, broken down by genders and by age. So it's recommended a moderately active male will need to take 2,700 kilocalories. If you are this person who's eating 2,700 kilocalories of food, you must do something that will expend more than 2,700 kilocalories. So here's a table of the ways you can spend energy. The mere fact that you are living, you will be expending energy. Even when you are sleeping, you require about 60 kcal per hour. Of course, when you're doing more physically active activities, you will expend more energy. So if you add up all these things within a day, and if it exceeds the amount that you intake, you will inevitably lose weight. As a bonus for you, for being in this class, which requires a lot of thinking, about 300 calories used by the brain a day. And it turns out if you were thinking hard, it boosted by 1.5 calories per minute. So of course this principle of nutrition was taken on by a nutrition professor who experimented with his own body by eating only snack food, but he limits his calorie intake so that he expends more calories a day. And doing this, he actually did lose 27 pounds even by eating a bunch of sugary, fatty food. Of course, this principle just proves that you will lose weight if your net calorie is negative. It doesn't mean you will have a healthier lifestyle. Alright, so by the end of this lecture, you are able to do the following things, like classify examples of matter. You can identify states, physical and chemical properties and changes. You know about the temperature scales and converting between them. You can identify different forms of energy, potential, or kinetic. And you can calculate the energy in food.